we're going to talk about today is the Edwards Reef Complex. Talk about both bandwidth extension and pre-stack inversion to rock properties. Okay, first off, our motivation. We'll talk about that. Then the geological setting, bandwidth extension methodology, and some examples. The rock property inversion and analysis of those results, and finally conclusions. Our motivation is to try to improve resolution so that we can see the geology and the reservoir better. We want to identify high porosity zones, and of course we want to increase successful drilling and profit. Our Edwards geology and plays. The Edwards geology and plays involves it's a reef complex with a progradational sequence with a repeating grainstone and reef facies, and that grainstone is going to be our main target. That's what we want to be able to identify as the grainstone. And the porosity is developed by both dissolution and through diagenesis. Our stratigraphy, and we're working with the Cretaceous, and in particular we're interested in the Edwards, which is in the Albion. So, and our primary focus is going to be the Edwards B. The other areas, the other targets of interest might be the Austin Chalk, the Eagleford, and the Pearsall and Sligo. But we're going to focus on the Edwards today. We have wonderful reef builders back in the Cretaceous period that did just a wonderful job for us developing porosity. You can see here the various different Rudis, these Cretaceous bivalve reef builders. And here's some cores and blow-up of cores showing one of those such bivalves. The traditional exploration method in this area was to go in and interpret the facies from the known seismic, and then use your well, from known wells, I'm sorry, I had it backwards. Use your well data for your facies identification. FMI logs is typically what they would use. And then you would take the seismic and then try to predict those facies changes, where they occurred, where they pinched out, that sort of thing. So you could create structural and facies maps. And then you would drill the best interpreted prospects. What you would do at this point is drill your pilot hole, run your FMI log, identify your facies and where your porosity is, and then drill a lateral for production. They had very mixed success. Probably, I think they told me they estimated around 33% success rate in this area. The new additional tools that we bring to this is we brought higher resolution seismic data for those facies mappings, rock property inversion, so we could actually identify the different rock types and where we think the porosity is, and therefore give a better description of the porosity, and ultimately porosity geobodies that could then be used to identify potential well locations. They had a much higher success rate. It's in the low 90s. So far, it's been very good. Hopefully that will maintain. So now I want to talk about bandwidth extension, its methodology, and some examples. Bandwidth extension is a key component of the success of what we did here in this Edwards Reef Complex. Now the B methodology, first off, we conduct a time series analysis in the continuous wave transform domain. So we break down both time, frequency, information so that we can have some time localization along with the frequency localization. We then compute harmonics and subharmonics of the fundamental frequencies. So the fundamental frequencies are going to be those frequencies that make up the signal that we see in our seismic data that we have a good signal-noise ratio of. And then we're going to compute harmonics, and the harmonics are going to be for extending the high end, and subharmonics for potentially extending the low end. Then we apply a convolutional-like process between the input seismic trace and the harmonics and or subharmonics to extract the signal. We still have signal out there beyond what our fundamental area that we're working with, and what we're trying to do is use these harmonics or subharmonics to bring out that reflectivity by extending the bandwidth of the seismic wavelet. The result is a broadband data which gives us a better structural and stratigraphic interpretation. This is just showing you the continuous wavelet transform. If you're familiar with the CWT, this is a very familiar equation. You get an equation function back of two variables, time and scale. Scale is approximately inverse frequency. It's easy to think of it that way. So you take your time series, which is your function f of t here. This is the scale parameter, and we're weighting the wavelet that we're going to use. This is our wavelet, and we use its complex conjugate. And we scale it so that we normalize the energy, because we're going to use different scale factors. This is our scale factor, which is about inverse frequency. And as you can see, this is a convolutional operation. So we're going to convolve a whole series of different scaled wavelets on our time series and get back a function in terms of time and scale of our complex function that tells us what our amplitude and phase is. Now, this wavelet, which we often refer to as the mother wavelet, has to meet the immiscibility condition if we intend to use this wavelet for reconstruction. So if we're going to take this signal, do something with it, and then bring it back, in order to reconstruct it, our wavelet choice must meet the immiscibility condition. And it basically says you have to have finite power. So that's the whole point of this thing here. This is the Fourier transform of your mother wavelet. So you're looking at the magnitude of that over its wave number. And the immiscibility condition basically implies that you have a zero mean and that the area on your wavelet is zero. So basically that you have a true wavelet. The wavelet we're going to use, because it has certain properties we really like and there's ideal for analyzing seismic data, is the Morley wavelet. Morley was a geophysicist, and this is precisely what he was looking into. And what he did is took a plane wave and modulated it with a Gaussian. A plane wave, obviously, because it goes on for infinite time, could not be an immiscible wavelet. So he put a Gaussian envelope on that. And if you use a wave number somewhere in the neighborhood of 5 or greater, then you're okay. You meet the immiscibility condition. So this is just showing you the real component and the imaginary component as it's a complex wavelet. And here's its time domain representation. This is the solid line is the real, imaginary line is the dashed, and here's its Fourier transform, so its frequency representation. This is just the reconstruction formula. It is a double integral because you're going from now a function of two variables to a function of one variable, which is back to a time series. This is just showing you that function. Again, this comes from your immiscibility condition. So the methodology that we use is, and this is a little cartoon we have. So you never see a spectrum like this, but this gives you an idea of what we're doing. You have your fundamental frequencies, this right in this range right here. These are the frequencies we have very good signal-to-noise ratio on. We pick what we call a pivot frequency. Then we go back an octave. So we pick up an octave of information. And from that, we can compute harmonics. So we can compute our first and, say, second harmonic. In the process, we're going to convolve this. And I say convolve loosely, because in the CWT domain, convolution is not defined, and it's not a true convolution anyway. But it's similar to one. So the easiest way to think of it is a convolution. So you get this output that is not completely out to where you went in terms of harmonics. The reason for that might be because there was a field filter out on the data, because we're trying to avoid Nyquist wrap around, and we're doing Shannon sampling, and we have to put a filter on there, some with a steep octave taper, somewhere before Nyquist to ensure that we don't wrap around Nyquist. So that's going to limit us. There could be some processing that was done that was very frequency dependent and basically eliminates any data out there where it has a very high fidelity filter, such as a resampling filter that you apply before resampling your data. So there could be a number of reasons why we can't go out as far as we'd like to. It may even be source related because it's vibrisized or something of that nature. Okay, and then we have our pivot frequency that we look at our low end. So if we want to extend the low end, we need to go up an octave. That's where our fundamental frequencies are. And when we extend our subharmonics, of course they get shorter because as we go lower, our harmonics are smaller, or our octaves are smaller in frequency width. And then again, you may have just a filter at the low end, or typically you just run into problems with ambient noise. If you try to get below 6 hertz, you start running into ambient noise problems, tidal effects, who knows what else, what all is out there. The trucks driving down the highways or whatever, who knows what that ambient noise cause is, but it's there, and it's hard to get rid of. So then you end up with a final bandwidth which is much broader than what you originally had, and there's a lot of benefits that result from that. So we're going to look at some of those benefits by looking at actual examples. So here's a data set. It's kind of hard to see. Sorry about that. This is the logs going in, and here's our synthetic trace, and the seismic data with the red trace is a composite. This is Hampson-Russell. I'm sure most of you are familiar with it. This is a Hampson-Russell display. This is our cross-correlation. It shows that we have a very good linear correlation, but also, you could almost get a fairly good linear correlation on either side of this just by moving up and down. So that would suggest this data is kind of ringy looking, which when we look at it, we'll see that. Here's the bandwidth extension result. It looks very nice on the cross-correlation. It's very well behaved and is telling us that this correlation is very unique. The cross-correlation is. And you can see that we are tying with our synthetic fairly well. And much more frequency information being shown here. So this is a comparison of the spectra. There's the input spectrum, the output spectrum. You see we went from, we went down about 5 hertz, and we increased quite a bit on the high end. About 70 hertz, I think it was. But you can see here, this is the extracted wavelets. We put a little bit more confidence in that. And this is the synthetics overlaid on top of the input seismic data. And like I said before, you can see that this has quite of a ringy appearance. This is from Mid-Con and in Oklahoma Panhandle area. And you can see that it has this very repeating-like sequence. Whereas here, once we increase the bandwidth, we're getting much more detail. And we're seeing that the synthetic is matching fairly well with the detail. So we got a fairly good match there. This is a look at the data prior to stacking. So this is after migration, prior to stacking. Because all the examples we've been looking at is post-migration. And this is looking at it from the standpoint of what can we do with bandwidth extension if we applied it beforehand to help us to do our inversion work. And this in particular is an example where we were looking at the Woodford shale play, which is very similar to the Barnett, which you've probably heard of. And here is our event of interest right here. This is on the input data, and certainly we can see the effect of coming out of this carbonate here, which is the Mississippian, into a shaly sequence. But the actual Woodford is this event right here that you can see on the bandwidth extension data. It's only about 25 to 30 feet thick in this area, I believe. And so we can actually see the top and base of this Woodford interval. This allowed us to go and do inversion all the way through density. And on this particular data, the density map matched with the EURs. Wherever the lowest density was in the Woodford Shale, we had the highest EURs predicted. And when the density was high, the lowest EURs. And this later we found out correlated to the fact that density drops with kerogen content, so in a linear fashion. So the lower your density, the higher the TOC content of your shale, which then made perfect sense as to why it was mapping to the higher EURs. This is an example of applying bandwidth extension. We just recently started doing it prior to migration. And you can see a number of channels here. This picture is kind of washed out a little bit, but this is a semblance. And you can see a number of channels that are showing up. But this is a Kansas data. And here they did a facies analysis of Poisson's ratio versus sweetness. And in their facies analysis matched up with what they had from their well control, where this is an eroded highlands area, and this is a stream valley, and this is a coastal plain. So they were quite pleased when they saw that. This is an example of gather. So now we're going to look a little bit more at the Edwards here shortly. And this is actually from the Edwards play that we're going to be looking at. And this is our normal bandwidth conditioned PSTM gathers. And you can see right here, this is the zone which the porosity exists. And this is actually gathers from a high porosity zone area. This is the bandwidth extension of those gathers. And now you're starting to see top and bottom of that porosity zone, which we couldn't see before. This is the same data area. This is the normal bandwidth seismic. Our target is right down in here where this big trough is. And here's the bandwidth extension seismic. And our target is actually right in here, right before you get to this lower trough. This is where the Edwards B porosity appears in the carbonate. Yes. Oh yeah, yes. Good idea. I should have done that. So this is our normal bandwidth tie that we have, and it has I think next slide says about a 71% correlation. Our Edwards is right in here, Edwards porosity. There's the extracted wavelet and the correlation with about 71%. This is the bandwidth extension. And you can see that zone now is much tighter than before. So the synthetic versus the seismic, we got a good tie. And it was about 70% correlation, so about the same. The phase on both of these, the wavelet is off a little bit, but we tied the phase with a VSP, and we have a lot more confidence in the VSP than we do the well. There was very little well control in terms of logs in this area. They typically would log just the zone of interest, but we fortunately found at least one that covered most of the area. So then we're going to go on and move to rock property inversion and the analysis of that inversion. Now when we talk about rock properties versus AVO, AVO, as we are probably all well aware, is rock property contrast or reflectivity information. And you're really looking at the difference between two layers. And what is layer one and what is layer two? We make certain assumptions about it. Maybe from geology we already know about the area, from well control, or just from marker beds and so forth, and using our creative minds and figuring out what we think is going on. and also looking at the AVO behavior, saying it's consistent with the shale over a sand or something like that. But there's always issues, and we often in the hard rock country, I would hear people say, well, AVO doesn't work. And what they should mean by that is AVO doesn't work as a hydrocarbon indicator in certain areas. And that's because the difference between the velocity changes from fluids of brine versus gas, your best case scenario, may only be 300 or 400 feet per second, whereas I can change the lithology of a shale and get you 300 or 400 feet per second difference. So I'll give you a lot of false indicators of pay when there's not. But that doesn't mean the AVO is not working. It just simply means that we can't use it as a hydrocarbon indicator. What we can do is we can take that and do a broadband pre-stack conversion, take our AVO information, and then try to get it to a point where we can determine, based on rock properties such as the VPVS and density, that, okay, we're likely dealing with a shale here, and we're likely dealing with a sand. So we can get rid of some of those uncertainties, or at least to eliminate some of the risk involved in trying to interpret what's going on. So basically, you get the equivalent at seismic scale of your logs. So it's a seismic scale of logs versus the reflectivity response that you're looking at. So we are using a three-term linearized Atkins-Richards equation, and which I'm sure you're all very familiar with. And let me finish my cartoon here. And as we say, the far angle response is key to understanding what's going on in your seismic data if you want to do inversion. And in particular, if you want to go after this term right here, your density term. And that also means that you have to have stable input gathers coming in. And one of the approaches we're using is with bandwidth extension and then filtering it back to a common bandwidth. Since we've extended its bandwidth, we can get that gather fairly stable and deals with at least some of the NMO stretch problem, which keeps us from going after density. Our pre-stack inversion workflow, this is just a mock-up of it. It's not exact, but it kind of gives you an idea of what's involved. We do use wells. Wells are our boundary conditions, in effect, because we don't know what our boundary conditions are at every trace. So we have to have some set of boundary conditions, and we can at least use the wells for that at certain known locations. Then we have our seismic data, of course, and we use the bandwidth extension on them. Then we go ahead and do our simultaneous inversion to the Atkins-Richards coefficients, so you have your VPVS and density reflectivities. Then invert these with good old impedance type inversion. Combine it with a macro model that you built, and there's a number of ways one can go about doing that, and it never seems to be the perfect way, but that's one of the things that you try to do is build that low frequency model for the component that you don't have and combine them together to get your broadband rock properties, which is what we're going to look at here shortly. And from that, if you can get all the way out to density, then you can look at rigidity, Lemay's modulus, or constant, whatever you want to call it, Young's modulus, bulk modulus, and so forth. So here we have an example of that inversion. This is the VP log overlaid on top of the VP inversion. Our target is right here, in this red and yellow. This is our Edwards B porosity zone. So this is the VP with the overlaid VP log. This is the VS. Now the VS is an estimated shear. We did have dipole shear to work with in the Edwards, but not in this location, not this survey. It's very hard to get dipoles or sonic scanners nowadays, but we try. I did have something up in the sands. It just didn't have anything down in the carbonates. Well, what VS log is this? This is an estimated VS log, estimated from the VP, using an estimator from the Edwards, but not from this survey. But I was able to estimate the sand portion of it, which is every part, but that's not what we're interested in today. Okay. Now, this is the density log and the density inversion. And you can see here we're doing quite nicely. And yeah. So there is our Eagleford Shale, by the way, upper and lower portion of it. This is the cross plot of density versus bulk modulus. And this is the area that we identified as our best porosity region for geobodies. And this is the well control. This is a well that they had to drill. All these wells on here were drilled after the work was done and was drilled based on this work. They had to drill this one because of lease requirements. We predicted it would be poor in porosity. As a matter of fact, another plot I'll show you here shortly, we did predict some porosity there, but that it was not one of the best areas, and it turned out to be about 300 or 400 MCF per day, which is marginal. But they had to drill a well here close to that location because of lease requirements. They were forced into it. But all the other wells that they had drilled have encountered good pay, and they drilled a couple of their best Edwards wells. I think this one and this one was their best Edwards wells that they have drilled so far in terms of production. That's geobodies. I'm sorry. These are geobodies that were identified, and this is a 3D view, and this is the seismic underneath. Yes. That's from that cross plot. So these are the geobodies that were generated from that. They drilled 9 wells in here, and all the 8 that are in the geobodies, every one of them was good pay. And there's just another view of those geobodies, kind of give you a perspective of where they are in relation to things. This is the porosity, overall porosity zone. So this is where you're going to have porosity pretty much in the whole area, which covers a good part of it. It's often been referred to as a potentially unconventional gas field. One thing I did mean to mention up here, whoops, too far. Let me back up. Yeah, this is a known field right here that they gave me a couple wells out of this to work with. And this field was known. This one they did not know about. And actually they didn't think there would be anything in the Edwards B in that section of it until this work was done. Let's mention that. So this is the overall, where they have porosity overall. And it's actually, there's a fault that comes up around through here, so it's sort of bounding this area, a very large strike-slip fault, and there's a couple more faults in there. And this is another perspective. This is a slice here, and these stippled points here, or dots, is where that good porosity, the highest porosity geobodies are showing up right in here. And this is the bulk modulus. These are your shales right in here. Actually, all of this is, and it gets kind of limey in the middle, as it's indicated by here by our higher bulk modulus. And this is the density. And again, this is where our geobody was for highest porosity. And this is Young's modulus. So this would be, up in here would be your Buddha and your Edwards A, which are both tight in this area. So conclusions. The broadband seismic sees the geology better, as we saw with the bandwidth extension result. It also enabled better inversion in this area because we couldn't see the top and bottom of the Edwards porosity prior to applying the bandwidth extension. The Edwards Reef porosity and sweet spots have been identified. The success rate has improved from around the mid-30s to the upper 80s or low 90s, somewhere in that neighborhood, depending on how you count. And the well planning has been very effective. That's the feedback I'm getting from my client. And the technology applied did properly offer valuable information for exploration and production. And that's it.